It is a pleasure to speak here, and I also really appreciate that you're bridging here the scales, so to say, between Europe or Germany and to India, which I think is really more than needed in times where we have more polarizations starting in the world again. So let's hope that science keeps us together for long. Now talking not about the current crisis, but about the past one, I'll talk a bit about COVID, but mainly on spreading dynamics, and especially spreading dynamics and information processing in the brain. I would like to start here with a video, and I do hope it shows, which shows here the brain of a zebrafish larvae. It's the top imaging, it's imaging the zebrafish larvae brain from the top. It's the two eyes, you see them at the top and at the bottom. And the activity is continuously active. It's made visible by fluorescent imaging of calcium imaging. Sometimes you see even these large bursts that then elicit the entire brain. And looking at the type of dynamics, there had been, because I can go into medias res here very quickly, there had been the hypothesis that indeed these brains should operate close to a critical point because that could be of advantage for information processing. When investigating these type of networks, however, we meet a number of challenges. The zebrafish larvae already has about 100,000 neurons, and the human brain has about 80 billion. 80 billion, that is 10 times more than we have people on Earth. So on the one hand, it's a large number. Compared to the thermodynamic limit, again, it's a very small number. Every single of the neurons has 10 to 10,000 connections. It really depends on the brain area. How are these connections built? They are built by cables, axons and dendrites, they are called. So a neuron is active, it sends an electrical signal over one of its sending cables. And only if another neuron has a receiving cable really connected to the sender, then it will also receive that cable. And that are these connections, the so-called synapses. And now the interactions between these neurons, they're not continuous. They're not like classical physics. They are pulse-like. So a neuron is active and sends a 1 millisecond short pulse, a spike, and it sends it out over the cables. There's about one of these pulses per second. So you can think of them as small explosive units, so to say. The interaction between the units is directed. So if one neuron has its sending cables, sends a signal, another neuron needs to put its specialized receiving cables nearby with a synapse. And the other way around, there is no way that the signal will travel except if they have established really, again, another connection. We have time delays in the connections. That is, a neuron is sending the pulse, it travels over the cables with finite time. So it takes a few milliseconds until it really reaches the receiving neuron. And what makes it most interesting, but also challenging, is that all these connections are changing over time. They are plastic. We know that from deep neural networks, the training in deep neural networks is done by changing the connection strength, the connection weights. In the brain, this changes are believed to happen autonomously. It's something that is the basis of emergent properties. And it makes it, for us as researchers, a bit more difficult to investigate this highly non-equilibrium dynamical system. Last but not least, if you observe such a video as I just showed you and the activity spreads over it, we are still faced with a very high dimensional connection topology. So the underlying network is high dimensional. Therefore, two neurons that are near to each other, that they're close by neighbors, it's not necessarily clear that they are directly interacting. They're only interacting if there's a dedicated cable between the two. And therefore, it's hard to estimate which two or which pair of neurons is or is not connected. It's not that one can't estimate it. People do that with electron microscopy, but it's very difficult. It is like looking at into, let's say, your plate of spaghetti. You know there is continuous spaghettis, but it is extremely difficult to just follow them by looking at them from the top. So we have a challenges with these experiments on the one hand, but on the other hand, new recording techniques nowadays enable us to record the hundreds of thousands of neurons in parallel, something we have not been able to do in the past, let's say 10 years ago. What I will do in the following is I want to formalize and show you how we investigate spreading of activity in such networks, and especially how we investigate that if we still only see a tiny fraction of it, so our subsampling theory. We'll then show how adapting the collective dynamics and computational properties to task requirements might profit from being close to critical dynamics. And last but not least, I show the self-regulatory mechanisms, so-called homeostatic regulation, that brings the network, as you will see, either close to a critical transition or farther away from it. As I said, the human brain has about 80 billion neurons. The mouse still has about 80 million. And recording techniques got much better. And here you see these neurons with its cables, ascending and receiving cables. But in experiments, we still only record a tiny fraction of it. And if you only record a subset of the neurons with sufficient temporal precision, that can lead, when we want to estimate the spreading of activity, that can lead to misestimations. And what we have done is a bias-free inference. I've been working on the topic of how to infer from this very tiny fraction of a system, how to infer properties of the full system for quite a while. I can only give a short glimpse here. It's topics that address not only neural networks, it's also a challenge when we think about disease propagation, where the dark figure might be high. In protein networks, we might not know all interactions. In social, economical, ecological systems, a lot of links are missing. In many of the systems, we observe something like spreading dynamics. And I would here now explain them with the example of COVID, because that is really the easiest. Spreading dynamics and branching processes date back to Golden and Watson in 1875. So it's quite an old concept. They quantified the following question. If there's, let's say, an infected person, and that infected person in the next stage infects a random number of persons, then there might be a chain of infections spreading through the system. How can we describe that chain, and how can we define whether or not this chain is critical or subcritical? Here on the right-hand side, you see the mathematical definition of such branching processes. The activity at a given time point, so really the number of people who are infected at a given time point t, that depends on the infection in the previous time step. Every single of the active ones in the previous time step, they do infect a random number y. So a random number y of units that can be 0. Most of the time it will be 0, 1, 2, 3, or maybe also in a super spreading event, very many. There might be additional infections coming from abroad. And overall, this now is an autoregressive process on expectation of order 1. What matters for the spread is not the distribution, or what matters mainly for the stability of the spread is not necessarily the distribution of here the number of infected people, but what really determines the stability or instability of the spread is the expected value of your random number. So how many persons are infected on average by a single infected person? And that is what we all now know as the R value. If the R value is smaller than 1, we are in a subcritical regime. Case numbers would decline exponentially. If R is larger than 1, we are in a supercritical regime. Case numbers would grow exponentially. And the critical state separates the two. In more complex systems, so this is just a branching process. If you think about more complex network, you can think about the R value as the largest, the real part of the largest eigenvalue. And that determines stability, linear stability of that system. So it is the R value that tells us whether or not such an infection chain will increase exponentially or die out. In neuroscience, we are very much interested in that critical state, as we come to later. Now, we would like to know what this R value is by looking and investigating the observed some activity, either some COVID spread or some neural data. And there's classic estimators, because on expectation, the definition of the branching process is the autoregressive order 1 process. The linear regression brings us an estimate. So we take the sampled activity at one time point, at the next time point, and the linear regression here is an estimate for the R value. The offset here is the external positive influx. And that works perfectly well if we have full access to the system. But let's assume now that we do not have full access, but we are missing a fraction of the dots. If we are missing a fraction of the dots, it's much more difficult to estimate the spread. I want to illustrate it here at the 3 examples. Imagine there were just 3 measurement electrodes, and this is, in quote, how bad the situation is in the brain. If there were just 3 measurement electrodes, we would hardly see anything of the entire spreading dynamics, but all we would see is some time series, some binary time series at the measurement electrodes. And if we then use the classical estimator, here now for subsampling of 10% of the activity, then the slope is not anymore a consistent estimator from R, but it is biased. Why is it biased? It is because the sampling process in itself adds variance. It adds variance to the observation, and that reduces here the linear regression. How can we overcome that? Oh, I should say that if already things like here, the correlation or covariance strength is biased under subsampling, then obviously other measures are also biased. And I want to stress that because a number of conclusions, especially in neuroscience, have been drawn by just looking naively on a subsample system without understanding that there's fundamental changes. The ansatz that we took is the following. We generalized the estimator, not only at AT and AT plus 1, but we looked at arbitrary time lags delta t. This is basically the autocorrelation function for the subcritical systems. And from that autocorrelation function, we find that there's a systematic bias, but that bias factor is independent of the delta t, and therefore we can partial it out. The derivations are in all detail here in the supplementary material. So to summarize that, if we only see a fraction of the system, then the naive or the classical estimator fails. It underestimates the spread in the system, and therefore the control parameter of the dynamics, the R value, is typically underestimated, and we found a way to overcome it. The good thing is this approach directly returns for us the control parameter R instead of just a binary test for or against the criticality. Why do I put this contrast? It's a point I can't go too much into, but you might be here familiar as in the seminar series that people very often have looked at avalanche size distributions and checked whether or not they follow a power law, and that would be, for example, a binary test for or against criticality. It has been also the classical approach in neuroscience. In neuroscience, in general, we only require knowing the sampled activity at each time step. We do not have to know what is the system size, nor the number of sampled units, nor any of the moments of the processes. That makes it very easily and very generally applicable. Under ideal conditions, we can even estimate the control parameter in a recurrent network. If we map this onto a recurrent network, from just looking at a single unit, we basically look at the return times and the autocorrelation function of the return times. From this, we can derive what is the branching of the activity in that randomly connected or fully connected recurrent network. This has been adopted by colleagues because it's very easily applicable, and I'll show you results that we have on that. Let me skip this part. I think with showing you that we investigated here spreading dynamics and phase transitions, and especially in this very simple example I showed you, managed to derive an estimator of how to infer the spreading. It is not a big surprise to you that when the COVID pandemic struck, that we had all the tools to estimate the spreading, that we had that basically in our drawer and only had to replace the neurons in our model by some virus spreading through a social network. I want to make a very short detour about our work on COVID. We have very early on quantified the effectiveness of interventions in the first wave. In the first wave, we knew very little about the pandemic. We did not exactly know what's the case fatality rate or the infection fatality rate, but nonetheless, we could use a Bayesian framework to infer how much related to each of the interventions, like closing schools and having a full lockdown, closing stores before, how much the R value, this is basically here the spreading in epidemics, how much that decreased. We then went into the question of whether test, trace, and isolate, how well this can mitigate the spread. We looked into the progress of vaccination, and the underreporting. And one point I want to here focus on, because it's our most recent work and this also defines our future work, is the infodemic and pandemic info interaction.